Sounds good. Hey, can you hear me all right?
Sure can.
Cool. All right. So thanks for joining everybody. We've got this is a study I did about probably 4 or 5 years ago now. And we actually just recently went back and updated some of the interpretations and stuff too. So we did a big poster on this back in 2017 through APG. So if you're interested in that, I can send you the link or actually probably a copy of the poster as well. So yeah, with that, let's just go ahead and get started. So for today, we're going to go through a really quick introduction, just a couple slides, talk about the methods for this, which is pretty straightforward, and then we'll then go into the inert gas relationship. So how we went through and kind of looked at this different gas data and how I honestly kind of typically go in every gas system, and then finally go through the interpretations. Where do we think the gas is coming from? How do we think it's migrating both laterally and vertically through the stratigraphy, and then wrap it up with like a big picture, like putting everything in at once. And then we'll finish out with just a couple implications. Most of these are pretty obvious, and then a couple conclusions. Okay. So over the last couple of years, really the last 5 years, there's a pretty big renewed interest in helium since we're kind of getting to this lower for longer natural gas prices. So right now, it's really hard to track down the data. But since the Bureau of Land Management kind of went offline and quit selling helium to the public back in 2019, 2018, helium has gone up. Right now, it's running at about $150 an MCF. Depends on kind of who you're selling to and what part of the country in. But you can think of this as helium, even though it doesn't make a huge part of your gas stream. A really high helium field is maybe 8%. But for every 1% of helium, you're effectively getting another $1.50 per MCF gross revenue. Not taking into account the extra equipment and stuff to get it out of there. So there's really two main areas of historical helium production in the U.S., which up until recently has been pretty much the only helium producer in the world up until about 10 or 15 years ago. You have the Greater Anadarko Basin, so think of Texas Panhandle, Southwest Kansas, and Oklahoma Panhandle, and then you have the Rocky Mountains. So the Greater Anadarko Basin, you get up to really about 3%, so you don't really get huge helium percentages in your gas stream. But the good thing is it's over very, very broad areas. I mean, talking about hundreds of square miles. And it's also relatively predictable. Although you definitely see changes in the helium content as you go through the stratigraphy or across areas, it's really not extreme changes. You have a pretty decent idea what you're getting yourself into, and that stuff's been produced out there for literally since the 20s. Okay. On the flip side, you have the Rocky Mountains. And the Rocky Mountains, unlike the Mid-Con, is all of these little tiny discrete fields that are just kind of scattered all over the place. That being said, you can get up to much, much higher percentages. So like Harley Dome, which is going to be just on the edge of our study area for today, these guys are getting 8% helium from a company called ICX Energy out of Dallas. So, prices right now, you're looking at an extra $12. Excuse me, that's not right. No, that's right. $12 an MCF just off the helium alone. So, and the other thing too about the Rockies is very, very variable. Unlike kind of Kansas, where you can just kind of go across, 20 miles and maybe the percent, your helium changes 0.5%. In the Rockies, you're going to see it go from 8% to 0 in a matter of miles. A lot of times, these are usually typically tied to like structural traps in the Rockies, especially. So if you go out there and actually look at the helium literature, a lot more has been done in the last few years, but most of the papers concerning this really fall into two categories. One, it's field characteristics and analogs. Think of kind of the old RMAG publications that, just kind of go in and say, all right, this field produces from this reservoir, has this much helium, this much carbon dioxide, methane, so on and so forth. There's a couple field compilation papers out there too, but they're a little tough to find. And then the second one is usually the source of the gas. I would say 5 years ago, this was very, very highly contested of where the gas is coming from. It's still a bit controversial 5 or 6 years later today, but I would say it's more settled than it used to be. And what this usually gets down to is people trying to do some isotope geochemistry on the gases. So what do we know about helium? Well, it's very small, which makes it extremely mobile. It'll actually leak out of steel because it's so small. So helium, pretty much all the helium we're looking at is alpha decay, radiogenic decay. So it's 2 protons and 2 neutrons, right? Very, very small. It's also relatively rare. All helium, again, pretty much all helium that we see on Earth is from radiogenic decay. And there's actually not enough gravity on the planet to actually keep it here. So when helium actually hits the atmosphere, it actually is on its way out and escaping to space, which is kind of interesting. It's a noble gas, the smallest of the noble gases, so it's non-reactive. And it's also pretty easily detected if you get containers that can contain it. So to me, this sounds like a tracer kind of engineering background. And so what I've always wondered is that even if you're not actually producing the helium for economic purposes, historically, you got to think about 0.5% helium in a gas stream is what makes it economic to actually get a little extra money off of it, or I should say high enough to pay for the equipment to strip it. But even if you don't have that, what we really started on this is, can we use helium just as a tracer for basin scale gas migration, right? Regardless of the economics of whether we can do it or not. So what I wanted to do here is actually just test this hypothesis out in the Uinta, in the Piceance basins. These basins historically have a lot of gas production, even today, still producing a ton of gas, even though there's not a whole lot of drilling activity. You've also got a ton of well control. And a lot of well logs and stuff like that too. So both Colorado and Utah are great for public data. So for the methods of the study, it's pretty straightforward. We digitized data from the Bureau of Land Management's big gas database that they built out over 90 years. Pretty much did all the counties in the Piceance Basin, which is just on the east side of the state line. And then we only did actually 2 counties in the Uinta Basin. So when you're going to look at this maps, I didn't realize that until today. It's a bit of a misnomer. There is some Uinta Basin data in here, but it does not include the entire Uinta Basin. So just keep that in mind. So the data we digitized are these gas analysis reports, again, that have been published by the Bureau of Mines and later by the Bureau of Land Management. This was a program that was started in 1917 and continued to 2007. At the time, helium was in the early days. So again, kind of 1917, it was a major mineral. We were actually trying to find helium in the country to go to war for airships. They didn't get it online by World War One, but by World War II, there actually was enough, and there was a couple of these big blimp airships that actually were used in World War II. They didn't really take off as much because by that time, bi-wing planes had taken off so well that they just weren't really as critical as before. But anyways, there's a lot of really good data in this. And this is that data set we were talking about in the sponsorship that we digitized and brought together. So after we digitized all this, took out the extraneous values, incomplete records, a lot of this historical data, so you're going to get that, ended up with about 460 data points across the basins. Not a huge amount, but pretty good. Definitely good enough to do a study like this on. And then finally, we integrated that with the regional geology. Now, this data is kind of a dog's breakfast of geologic formation. So we're getting everything from the tertiary all the way down through the Ordovician. Okay, so not only can you just get this gas data, but you really need to understand the petroleum systems out there, and then and what essentially the petroleum systems is which source rocks are actually producing hydrocarbons, what's the typical reservoirs and trapping styles that you get, and try to kind of figure out, all right, is this helium and nitrogen and stuff moving through the same systems as the hydrocarbons, or is it a totally different thing? And then last but not least, once we put all this together, we just tested for a bunch of relationships. I kind of went into this originally just trying to learn more about it and see what was going on. So there wasn't any super big hypothesis of what we were trying to prove. It was mostly just poking around and seeing what came out of it. So for this, which we're going to step through today, is we're going to see gas versus gas. How does nitrogen versus helium stack up? Do we see any changes systematically through the stratigraphy or the stratigraphic position? And then also the aerial extent of the data. So I will put one note that most of the maps that you got on here, the The helium spots that are on there are actually going to be either Swanson's mean, or they're going to be the max value recorded in that well. The reason for that is because helium, the distribution of helium concentrations in the gas stream is actually log normal. So Swanson's mean is a little bit more appropriate to use instead of just an average, because it's log normal. So I think probably everyone pretty much knows what Swanson's mean is, but it's essentially just it's an easier way to calculate the logarithmic mean of a data set. So just a fancy way of saying the average. So the first part of this, once we digitize the data, right, we had to integrate this in with the geology. So if you go into the UN and the Piceance basins, there's 4 major petroleum systems that are defined by the USGS. There's the Green River system, which is tertiary lacustrine deposits. You're sourcing out of those lacustrine source rocks, and then your reservoirs are also in the lacustrine interval itself. So you'll get these like little turbidites in it, or you'll get some oolites that'll host it. And then sometimes this will actually drop down into the Wasatch Formation, which is mostly fluvial with a lot of like discrete sand bodies and stuff. So that's the first system. So again, this is kind of pretty much all tertiary. Next system down is the Mesa Verde petroleum system. So the Mesa Verde group is the classic. Actually, if you've worked in the Book Cliffs or gone to the Book Cliffs, those are included in the Mesa Verde group, or most of them are. So the Mesa Verde group is the classic, like big classic wedge that's building out from a thrust belt or from a mountain belt out into a foreland basin. It's a real dog's breakfast of reservoir types. You've got everything from marine sandstones. Probably the primary reservoir type is going to be these discrete sandstone bodies from the fluvial systems in there. It's typically pretty dry gas. Probably the vast majority of that gas being sourced by coal beds that are directly above the marine interval as it built out into the Western Interior Seaway. And it's relatively small migration distances. The next one is the Mancos Mowry petroleum systems. They lump these together. So the Mancos Mowry, this is the whole Western Interior Seaway in the Cretaceous, right? The whole middle of the continent effectively covered in a seaway. The Mowry is the first kind of shale interval that makes it in there. And then the Mancos is the main one. So thousands and thousands and thousands of feet of marine shale makes a really good seal for the basin. I think we've got very good evidence here that the Mancos is effectively keeping down inert gases down below it for most of the Western Interior. And then last but not least is the Weber system. So the Weber system is way down here at the bottom. The Weber is an Aeolian sandstone that it just barely makes it into the Piceance Basin. So out, again, northwest Colorado. The Weber is really thought more of an extension of the Phosphoria petroleum system. The idea is that it's the very, very tip of this long distance Phosphoria oil migration out of western Wyoming and kind of northern Utah areas. And that this was really trapped out here originally as a stratigraphic trap, and then later there were multiple structural traps that were created by the laramide orogeny in the tertiary. So if you want to go, and I'm not going to go into a ton of detail on this, but these USGS publications, 2003, these digital data series are really good. So I'll definitely encourage you to go look at those, or just shoot me an email. I can send over some key papers. Okay, so based off of those petroleum systems, we kind of want to do the same thing for this inert gas system. So when we first started looking at this in 2015, 2016, helium was just it was still at the time was really an oddity. There wasn't any, as far as I could tell, really systematic way to go out and search for it. So we kind of coined this term, kind of the inert gas system or the helium system, where essentially we're using the exact same concepts as the petroleum system, where there's a source rock, there's migration, there's trapping, and so on and so forth, right? Now, for us, these inert gas systems or inert gas families are based off of the petroleum system it was actually hosted in, because the idea is that if hydrocarbons move through the system, then probably the inert gases are probably utilizing it as well. Obviously, there's a functioning way to move fluids through the rock, right? So why wouldn't nitrogen and helium try to move through the same thing? So the way that we base these out would be the Green River system. Petroleum system, we just called this Green River Wasatch Inert Gas Family or Inert Gas System. Same thing for the Mesa Verde. The Mancos Maori I actually split up into two things. The Mancos B Frontier, which are sandstones actually hosted within the Mancos Shale. And then the lower interval, we called it the Dakota Morrison Entrada. These are these sandstone intervals that are all over relatively thin, talking 500 feet worth of different formations that are directly underneath the Mancos Shale. Now, they're typically rolled into the Mancos Maori petroleum system because the nomenclature here is where the hydrocarbons were generated, which is out of the Mancos. And the idea is that it's migrated laterally into these sandstones. So we're going to see a lot of this Dakota Morrison Entrada today. And then the last thing here is the Weber inert gas family. Again, this kind of extension of the Phosphoria. Now, I do want to show, I didn't make any slides on this, but I do have a spot fire project up. So these inert gas families, just to show you like how we can split these guys out. So here's a map of helium across the US. Obviously, hot colors are helium. We're really looking in this area here, so kind of northwest Grand Junction. But I really want to show you is this right here. So here we have helium. I'll reset this. Okay, so I have helium on the y-axis, nitrogen on the x-axis, and then methane is actually coming out of the board. Okay, so three-dimensional cross plot, nothing crazy. The big difference on this is the size of the bubbles. So the size of the bubbles here are CO2. So what you'll typically see in most gas systems, it's actually really a function of these four things. It's how much nitrogen's in the system, how much helium, how much CO2, and then hydrocarbons. And on the hydrocarbon side, is it dry or is it a wet system? But I will see if I rotate this around, you can really kind of see how these things plot out. So where you see this really high CO2, you'll typically get a lot of nitrogen and helium as well. And that comes at expense of the methane. So you got to really think of this. It's really kind of a I guess it's a four component problem. Is that nitrogen and helium are almost always associated with each other because of the way they migrate. And they're totally, I would say, mostly decoupled from hydrocarbons and for the most part, also completely decoupled from CO2. So when you see these different things hosted in the same system, especially like with elevated CO2 greater than 10% or nitrogen helium greater than 10%, I would argue that you have competing gas systems, these inert gas systems competing again for reservoir space on for your petroleum systems as well, whether that's oil or natural gas or a combination of both. Okay, so we're going to go through a lot of maps today. So the first one here, this is just a plot of all the data, get y'all familiar. Okay, so I have an inset map out here. So this is Colorado, this is Utah. The red outline is the area that we're going to be looking at. On the right is a blow up of that map. So green is the Mesa Verde group. Okay. And then the white space in between here, this is the deepest part of the Piceance Basin. And this would be the deepest part of the Uinta Basin. Okay. I've also got faults on here. Down here at the bottom here, this red are intrusions that have come up, which I think is probably the source of CO2. And then in the purple, you can see this is actually the Uncompahgre uplift. So Grand Junction, Colorado is right here on the edge of this. So this little valley coming across is actually where I-70 would come through. Okay. And Aspen is just off the page on the east side. So if we color those by those inert gas families, you see there's definitely kind of a sampling bias or aerial distribution of these systems. So the Green River and the Mesa Verde are typically in the deeper parts of the basin. That's because these are historically interpreted as basin-centered gas accumulations, or I guess for the Green River, it's kind of basin-centered oil accumulation too. Up here at the top in this purple, this is the Weber. So these are pretty much the only phosphoria oils in the basin other than some small fields to the northeast. And then this gray here is the Mancos Shale, which lies underneath the Mesa Verde. So this is actually an anticline that's actually been breached, isn't the right word. But the sandstones going over the top of the anticline have been eroded away. And so you've got this nice little valley in here that Chevron's producing oil out of. In red, we have this Mancos B frontier system. And then down to the south in yellow is this Dakota Morrison Entrada. So the first thing we're going to look at is the inert gas relationships. So now that we showed you this is the data set, this is how we digitize it, let's actually look to see how these gases are related to each other. So we're going to step through this in three different ways. First, we're going to look at the scatter plots. We're then going to look at stratigraphic position, i.e. young versus old, and then we're going to look at it on map view. So first, for the scatter plots, the one that I typically go to is helium versus nitrogen. And actually a better way to do this is actually log scale. I just didn't do it for this figure. If you look on here, we've got some pretty big outliers. And these are both from a field called Harley Dome. This was historically was a helium reserve for the federal government set aside in the 30s. There's a company operating it now. I don't know, it's pretty anomalous, and I'll talk about that a little later. If we take out those values and color this plot by the helium families, I would argue that you get two trends out of this data. The first one is in the purple, which is the Weber system. I would, just kind of eyeballing it. And then the second one would be this Dakota Morrison system. So now for this, again, these are just colored by the reservoirs, right? So I'm not actually taking this trend and going back and saying, oh, okay, because they're on this trend, they're all related. They're all in the Dakota Morrison. These systems are totally based off of the reservoirs that they're hosted in. Okay, and just again with all the data, I'd argue that you have these two trend lines that are in here. They're not great, but it's just something to look at. Next thing, if you look at the stratigraphic position, on the left, let's just focus on this one's first. I have the Swanson's mean. So again, more or less the Lognormal mean of all of the helium percentage for all the samples in the Weber. So this could be, and I should have that in here, again, with the 460, I believe we've got like 100 something samples in the Weber sandstone. Okay. So if we look at this as a function from older rock, which is on bottom, to younger rock or reservoirs on top, we can see as we go from older reservoirs to younger reservoirs, we have a pretty significant decrease in helium from 0.4, which is economic, down to 0.02, which is not economic at all. If we look for nitrogen, which is the center plot, we see the exact same thing. Makes sense because we saw on the last plot too that nitrogen and helium typically run together. But if we look at carbon dioxide, which is here on the left, you see a lot of carbon dioxide here in the Dakota Morrison Entrada. This is really with the Entrada reservoirs out here. And you see a little bit in the Mesa Verde. I'd argue that's associated with coal bed methane, but there's really no systematic trend. By systematic, I'm not saying we're not seeing CO2 increase as we go up or CO2 increase as we go down. The last thing we want to look at here on the relationship is the aerial extents. So we're going to look at this in three different ways. So here's that inset map that I showed y'all earlier. We're going to step through it first on the helium concentration, then we'll step through on the nitrogen concentration, and then finally the CO2. So first, let's look at the helium. So we plot all the helium data up here. Everything is sized by and colored by the helium content in the gas. Okay, so you can think of anything that's yellow or above is really good, at least from an economic standpoint. And I would argue, obviously, you get two clusters of data that pop out, and I'm just going to circle these just really roughly. Well, this top circle, if I limit the samples to the Weber inert gas family, they're all within here. So again, as I was saying earlier, this is phosphoryl oils that are sourced really pretty much in this one field. Okay, you do get a little bit of gas associated with that too, and that gas has got some elevated helium. Not huge, but for an oil reservoir, it's actually decently high. You don't really see helium associated with oil, I would argue, a whole lot. If we look at the southern circle that we threw just on the map, we can see this is actually related to this Dakota Morrison Entrada collection of reservoirs. Okay. So again, these are reservoirs that are hosted below or found below the Manco Shale and historically sourced by oils and gases out of the Manco Shale. Okay. Now, if we look at helium, we're going to see the really similar thing. So here's all the data again. Those are those two, I just copied and pasted those two circles, those areas of enrichment over from the helium slide. And we see it pretty much overlay perfectly, right? If we limit it to the Weber inert gas family, We're seeing Rangeley Field pop up again. And if we limit it to the Dakota, Morrison, and Trotta, again, we see this southern swath of fields samples pop up once more. And I will say, too, that these maps include everything, all the reservoirs. So like some of these wells are actually producing from multiple intervals. And so you can actually see multiple dots will plot up on the same thing. Again, if it has an Entrada test versus a Dakota test, they'll show up. Last but not least, let's look at the CO2. If we take those exact same circles as before and just plop them on here, what we'll notice is one, up in that Weber system, we saw elevated nitrogen and helium. We do not see elevated CO2 in here. Now, there is a caveat to this. Rangeley Field is one of the first CO2 floods in the world. Was started in the early 80s, late 70s, if I remember correctly. So these samples are before that period. So obviously you go out and sample it now. Yeah, there's going to be a ton of CO2 come through the gas. But yeah, so just keep that in mind. If we look at the southern circle that we created from the nitrogen and the helium maps, we'll notice for the most part, it actually works all right. But the problem is way down south here, we see absolutely no CO2 enrichment at all. Okay. So this is where CO2 kind of completely diverges from the nitrogen and the helium story, right? So again, try to think about just because these gases occur with each other commonly does not mean that they got there the same way or from the same areas. Okay, so the takeaways from all of this on the scatter plots, one, I would argue we get two, I maybe shouldn't put distinct, but I would say two trends show up in the nitrogen versus the helium plots. For stratigraphic position in general, helium and nitrogen concentrations are highest in the oldest rocks and lowest in the youngest rocks. And it's pretty systematic. It kind of stair steps as you go through younger stratigraphy. Although you do not see this with the carbon dioxide. Okay. And if you look on the maps, the highest helium and nitrogen are found in two areas. It's on the crest of the Douglas Creek Arch, which is this big green outcrop here. So I should have mentioned this earlier. Douglas Creek Arch is a basin scale kind of arch that actually high point that separates the Piceance versus the Uinta. So everything west of this is considered Uinta, and everything east of this is really considered Piceance Basin. Okay, so we saw this highest helium and nitrogen on the crest of the Douglas Creek Arch and at the nose of the Uncompahgre uplift, which is that big basin fault or big basin uplift that comes and creates the Colorado National Monument. But if we look at CO2, we also see high CO2 on the Douglas Creek Arch, but we do not see it on the nose of the Uncompahgre uplift. So again, showing that, yeah, maybe carbon dioxide is related to these other gases in some areas, but definitely not all of them. So gone through and shown you the methods, right? So how we got the digitized data and how we assigned it, step through the just kind of general relationships, nothing crazy there, just throwing everything against the wall and seeing what sticks. So the next step I'm going to do is kind of walk through my interpretations of where I think the gas is coming from and how it's moving through the system. And then finally, what that means. So like I just said, we'll go through the gas sources. I'm actually going to split out the migration into three different kind of collections of slides. First, we'll go through the lateral migration, then we'll go through the vertical migration, and then we're going to show it all at once so you can get kind of a 3D picture in your head. So for the gas sources, there is a lot of literature out there on all the potential ways to get these gases. Some of them are more common than others, and some of them can create larger volumes of gases than others. I've got this collection of literature up here. We'll send out this list to y'all if y'all want to really go down in the weeds. I've also got a lot of other stuff too. We actually just taught a short course on helium exploration yesterday. I would argue my interpretations for this is that the helium is coming from radiogenic decay. Now, some folks will argue that maybe it's coming from the mantle and you're seeing it in rift zones. The difference is really helium-3 versus helium-4. Helium-3 is what they call primordial helium. So think of this as comes from the Big Bang and really is leftovers from when the Earth actually formed as a planet. Do we see helium-3 in the real world? Yes, absolutely. Is it ever found in economic quantities? Not that anything I've ever heard or been aware of, right? The vast majority of, the vast majority of helium you see on Earth is helium-4, which is strictly through radiogenic decay. Now, where is that radiogenic decay happening? Probably in the crust, probably related to some of these big basement uplifts. At least the uplifts are probably a way to release some of the gases that are trapped in there. But it's mostly, you think of, it's going to be coming off of potassium, right? Whether that's K-spar in the crust or maybe a little bit in some of these source rocks too. For the nitrogen, again, there's a lot of different areas to get this from, a lot of different ways to get this. I would say for us, probably the most of it is from metamorphism and intrusions. And actually, these are pretty much related. The nitrogen is probably coming off of, it's typically associated with clays or some sort of ammonia that's in the system. And I believe there is intrusions down here. And I think these intrusions are actually degassing some of the basement via metamorphism, or maybe also driving off some of it from some of these sediments as well. I'm not as clear on this one, I'll be totally honest. That being said, nitrogen is so common, it's a lot tougher to kind of track down the potential sources for it. And then the last thing is CO2. Now, the CO2, I think, are also related to these intrusions. I should have this checked. But I don't think the intrusions so much are actually the source of gas, is that those intrusions are going through some deep old carbonate reservoirs in here, notably the Leadville limestone, which is associated with very high CO2 down in the Paradox Basin. So I think it's honestly, as those intrusions come up, you get metamorphism. So probably thermal sulfate reduction through the limestone, or literally just turning it into marble. I mean, there's the town Marble, Colorado, not far down the road for these reasons. And it driving CO2 off in the process. Okay, so we went through the gas sources. Now, how do we think this is actually moving through the system? So I'm going to go back to the scatter plot, and we're going to kind of go off of my little cocktail napkin drawing here on these two trends. Now, in the abstract, I had these called the Uncompahgre and the Uinta trends. And the reason for that is because originally we were kind of thinking that maybe the gas was actually getting sourced off of the uplifts themselves. In the last few years, there's a lot more literature that's come out about moving these gases through basinal brines, like long scale migration. And we had talked about that at the time, but weren't really sure, super confident. I think now, and you'll see in these next slides, I think we've got two different brine systems that are moving through the system. And so because of that, I've kind of renamed it so that what we were calling the Uncompahgre trend is now referring to as the Southern trend, which is just those Southern gases. And then this relationship we see with the Dakota, Morrison, and Entrada, which will actually onlap the structure, I should note. And then the Northern trend being these Weber reservoirs that we see up in Rangeley Field, again, associated with very long distance phosphoria oil migration. So I think the way that these gases are getting in the system is probably going through these aeolian carrier beds. We have aeolian stuff in the north and the south, right? So the Weber's aeolian, the Entrada is also aeolian bed. You've got really great porosity and permeability. They're laterally continuous to an extent. Neither one of those sandstones covers the whole basin, but both of them cover about maybe a half to a third of the basin, depending on where you're at. But again, they very much are laterally continuous. And both of them are actually topped by mudstones. Well, I'll show you some pictures here. So what's weird is the helium is very, very small, and it likes to leak out. But you'd be surprised how well some of these mudstones actually trap it. So my candidates for this is the Weber for the northern trend. Again, probably gas associated with the phosphoria, oil migration, and then Entrada Wingate sandstones for the southern trend. I think this gas is actually probably being sourced within the Uinta and the Pions and coming up through fault systems. So here's a photo of the Weber just to show you how much sand that we've actually got. And then the Park City Moan Copy, I think possibly kind of traps or seals, I should say, for the system. And then for the carrier bed for the southern trend, this is just outside. You can see Grand Junction in the background. This is on the National Monument. You can see you actually have Wingate, big, thick alien bed sitting right on Precambrian basement. Okay, so if we look at this in map view, I'm going to throw this off to the side. We're going to take that same map, zoom out a little bit. We've got the Uinta Mountains up to the north, Uncompahgre uplift to the south. We're going to look at this northern trend. So if we color these dots by helium and limit it to the Weber system, I think that northern trend is those gases are coming from the north and getting to the south. They get stopped here at Rangeley Field through the stratigraphic or structural trap. Keep in mind that these gases, because they're associated with phosphorial oils, probably moved in. I think they're probably moving in with the phosphoria oils themselves, not just in place later, which means they would have migrated out before the Uinta Mountains were here, or during the Uinta Mountains have gone up multiple times, but the Uinta Mountains would not have been a major structure at the time of migration. If we look at the Dakota Morrison Entrada IGF, inert gas family in that southern trend, really, I think we're getting these brines coming out through the basin down here. They're moving up through the alien beds, which are mostly found in the southern basin, moving up through the structure, getting to this kind of basin high, the Douglas Creek Arch, getting stopped here. There's a major structural trap here called the Douglas Creek Fault that offsets the Mancos Shale by over 1,000 feet in some areas. And then finally, carbon dioxide. I took that graph away because carbon dioxide wasn't on that graph. I think you're getting CO2 coming out of the basin for the Piceance, and it's actually getting stuck here by what they call the Gar Mesa Fault Zone, and that's why you're not seeing any CO2 down here. So although you do see CO2 in the Mesa Verde, I would say associated with the coals, you don't see it coming to the Uinta side. And I think I think that's good evidence that it's being sourced from the Piceance Basin itself. So for the vertical migration, we showed that helium is increasing with highest in older rocks, lowest in younger rocks. So I think probably what was going on is we have the Juana Lopez or the Maury are a shale at the very, very base of the Mancos group. And I think these are actually essentially a leaky seal for the system. So they slow down helium migration going up to the frontier sandstone, which is just above it, but they don't totally stop it. That being said, between this frontier and the Mesa Verde, you have the Mancos Shale, which is in some of these areas, close to 5,000 feet thick. I think by that point, you keep a very, very good top seal, effectively for the entire basin, with the exceptions of local areas here and there. And I think that's what's actually stopping your fractionation, or what's causing the fractionation as you go up. All right, so let's look at this in the big picture, and then we'll wrap up. So if we take the basin here, I'm going to throw up a seismic cross section, A to A prime. This is from Waker and Johnson. I believe it's 1989. Okay. I'm going to also throw up that scatter plot and then also throw up those bar charts too. We're going to look at this whole thing together. I'm also going to replace that seismic cross line with the figure that we digitize it, so it's a little easier to read. So I think for the southern trend, what happens is we've got gas coming up from basement that's getting in these older rocks, moving through these basinal brines and moving vertically probably up through these fault zones in the Gar Mesa Fault Zone. Where then, this arrow there should be two arrows, one going north, one going south. So I think from the Gar Mesa Fault Zone, which is right here where the A is, we've got some migration going up dip towards the Uncompahgre uplift, right? There's a lot of these little anticline structures that are superimposed off of this basement structure. And then we're also seeing gas go north along this Douglas Creek Arch, eventually get stopped by the Douglas Creek Fault. And because there's some normal faulting associated here, we actually get some vertical migration up through kind of the lower Mancos into the Mancos B reservoir. If we look at this for the Uinta, it's a lot simpler to look at because most of it's off the map, but essentially the same concept. We're basement, you're degassing basement into some sort of older formation. It's then migrating laterally with the phosphoric oils, getting trapped here at the Rangeley Field, initially by probably a stratigraphic trap. It's then trapped even better by a anticlinal trap that's been created during the Laramide. And so you get this really nice, clean anticline field with oil and a little bit of helium. So what are the implications for this? It's actually pretty straightforward. I think for all of these is that, at least for me, it gave me kind of a new understanding, maybe not new understanding, but like an enhanced understanding of how gas is moving around the basin, right? So what are all the different reservoirs that are connected up and how can it move through stuff? It's also really good for risk. Now, for the helium, there really is no risk here, right? I mean, the risk is you not making more money off of your helium stream. The nitrogen, there's definitely a risk for the heating value. Nitrogen has no economic value, right? I mean, it's 70% of air. And so if you got really high helium, it's you're actually going to get much, much lower revenues on your gas sales. And it actually get to the point where you might actually have to call it a dry hole. Nitrogen rejection units aren't cheap, so if you can't get it to pipeline spec cheap enough, it's just a dry hole. And some of these out here can get up to like 70% nitrogen, very, very high. And then the last thing is carbon dioxide. There's obviously a heating value risk here and a dry hole risk too. Again, just if it's the BTUs are way too low. And then also for CO2, obviously, is you've got an LOE risk, right? Carbon dioxide loves to chew up steel. So, you might be drilling these shallow gas wells that might only be 3,000 or 4,000 feet, but then you'll have to go out and put stainless steel or some sort of, maybe not stainless, but casing or tubing out there that has a special coating. It's going to up your cost. And the last thing is the opportunities. I put for CO2, there's opportunity for enhanced oil recovery. There's not a whole lot of oil production out here. So even if you source it, there's not really any place to use it. And plus, most of the CO2 in the US is really getting produced by there's a Doe Canyon down in southern Colorado. There's Bravo Dome in northeast New Mexico, and another one down there. I can't remember, but it is there available if you needed it for something. I would say the big thing is for the helium exploration. If you can find one of these really small anticlines, you can drill. They're usually pretty shallow. So you could definitely make some money off the helium, or better yet, you go buy up the whole area and go after it for volumetric kind of play, right? So even if the helium's relatively small, like the Mancos B, where it's less than 1%, there's hundreds or thousands of gas wells out there. So you could buy all that up and attack it by volume. When we initially pitched or were showing this, that was kind of what I had in mind. And there's a company called Utah Gas Corp that since then has actually gone through that business model and brought an old helium midstream plant back to life to go after that. And that's it. So conclusions, I think the UN and the peons provide a pretty unique look at the distribution of these inert gases because you have so many different petroleum systems, and because they're all pretty distinct from each other too. You can really see how all these systems are playing against each other and maybe utilizing the same migration pathways. Again, I'd kind of go back and renege on my old interpretation of that the source of this is really coming off of those local structures. And I think it's probably instead coming from more of this long distance migration versus these via these based on brines. It's really not that much of a difference than what we were saying before. But who knows? I mean, it's really tough to go through and track these things down without more data. So we don't get as many deep tests in the peons or the UNA as we'd like to get down to the really old rock, because these basins do get very, very deep. And so it's just kind of one of those things that until new data comes along, we just got to make your best interpretation possible. Last thing is, I think the carbon dioxide source in the peons basin, we've got a lot of intrusions there. I think it makes total sense. We got a lot of carbonates that has to pass through, and there are some deep tests on some of those carbonates too, where we see really high CO2 produced with them. And the last thing I'm going to leave y'all with is Harley Dome. So remember, that's that one, those couple data points that are way, way out into the ether, right? If I go back up to these maps, I'll show you the reason I think Harley Dome's actually probably paradox related, even though it's technically considered the Uinta Basin. This is Harley Dome, I believe this right here. It's just on the south side of that Gar Mesa fault zone. And there's no CO2 related to that field at all. Versus you go just 2 townships away, exact same reservoir, exact same style of trap in the Bar X field, which is this right here. Pure CO2, almost entirely CO2. So much so there was actually a dry ice company that was formed out here in the early 40s, I believe, just off of that field. So very, very different. It's kind of again, it's these little things that really, to me at least, really add a lot of value of how things are moving around. And as an explorationist too, right? I mean, you want to know those little details. Maybe there's some opportunity there you didn't see before. So with that, I'll take any questions. And I've got two. Y'all get the PowerPoint off this. I'll just show this real quick. Please afterwards hit me up on Linked Up. I'm pretty active, as Brian well knows. So, and with that, I'll yield the floor back.
Yeah, no, I mean, well, I'm going to go ahead and go through some of these questions with you, and feel free to use your slides if you want. But we'll start with the top, and just to respect everybody's time, we'll try to see if we can get maybe 10 minutes in. Just depends on how the questions are going. But other than that, thank you so much so far, Brian. It's been fun. So let's get rocking and rolling here. Was the poster mentioned in search and discovery? And there's a number here, 42098, and that's from Silver.
Yeah, that is the poster. I just looked it up just now. Yeah. So, we did this. It was 2017. So was it the 42098? If you go into like Google Scholar or data pages, just put McDowell helium, it'll show up. So we also did some cool stuff too out here with risk mapping, using kind of how we thought of seals and reservoirs and stuff like that, and made some composite maps as well. So it's kind of cool approach. I don't think anybody else has really done that, to be honest, for better or for worse.
All right. Next question is from Janelle Edmond. What is the helium percent in the Labarge platform?
I want to say Labarge is less than 1. I tell you what, if you send me an email, I can get you to the right guy. Labarge is really strange, though. Labarge is in regards that most helium production is coming from reservoirs that is high helium, high nitrogen. Labarge has, from my understanding, is relatively low nitrogen. You do get a little bit of helium, but it's associated with carbon dioxide and sulfur, H2S. That's actually from thermal sulfate reduction out of the whatever that lime is. I think it's Mississippian aged lime. Where the helium really comes from, again, probably degassing off a basement. But I can send you a ton of stuff on that. We were talking about this. My compatriot at NGDG was talking about this yesterday in our short course. So,
all right. We got a couple from Jim Tucker. I'll go to the first one anyways. Are there any surface gas seeps along the Douglas Creek fault?
I don't know. There's definitely oil seeps out there, but it's out of the Green River, so that wouldn't be helpful. You do have some gas seeps deeper in the Piceance, but that's from Mesa Verde. As far as along the fault itself, I have no idea. I don't know of anything off the top of my head. And honestly, too, the Douglas Creek fault, by the time it comes to surface, the displacement isn't huge. Most of the displacement actually peters out at the top of the Mancos Shale. I'd have to go back and look at that. As far as I know, though, there's no major gas seeps out there. Unlike you get down like around the southwestern nose of the Uncompahgre Uplift, you definitely see gas seeps out there, especially with there's a couple old wells that have been abandoned that actually will blow water and CO2 out every day or so. But yeah, that's the best I got. So yeah, if you want to, like I said, shoot me an email and we can do some digging. I can look at throw some publications to you.
Relationship between basement faults and helium and nitrogen. That's from Janelle Edmond.
Yeah. I think a lot of people tried to make those correlations, and it's really tough because I think normally what you're seeing you see helium in the US, you see helium associated with big structures that were effectively activated during the ancestral Rockies, or when essentially Africa smashed into Arkansas, right? So Uncompahgre Uplift, the Uinta Mountains, the Ancestral Rockies, like the kind of Ancestral Rockies Front Range, and then also the Anadarko Basin too. You have the Ouachita Mountains and all that stuff too. I think honestly, I think it's associated with those basins faults is probably because you're juxtaposing reservoir rocks next to big basement structures where you can degas some of that kind of helium directly into the reservoir. But also too is there's this kind of idea that you're actually essentially squeezing out stuff as like a toothpaste tube. So as you get these big structures, you're actually kind of squeezing those basinal brines up dip, and that's how you're getting the enrichment. You got to think the enrichment for helium is really long distance migration. It's like nitrogen in that regard. It's like Guinness, right? And Guinness, it's like it's really creamy because the bubbles are super tiny, right? Versus CO2, a regular beer is really big. It's the exact same thing. Nitrogen and helium love to stay in water. And so you have to get it up into shallow depths and get the pressures down to make it actually come out of solution. So sorry, that's kind of a roundabout answer, but is it related to those big basement faults? Yeah, I think partially, but I wouldn't say that it's a one-to-one by any stretch. I mean, some of the biggest helium stuff is way up in central Kansas. I mean, hundreds of miles away from like the Anadarko big basement bounding fault or basin bounding fault. So
thanks for that. Thanks for that response, Bryan.
Yep.
Next question I got from Jeff Aldrich. Have you looked at Model Dome Field in Los Animas County, Colorado?
Yeah, so I know, Jeff, you're asking the stuff y'all been working with Blue Star. Yeah, I mean, there's good helium down there. From my understanding, there's next to no pressure, though. And there's not a whole lot of well control out there, too. I'm sure, as you know better than I do. I think, honestly, probably even better areas to go up northeast towards like Cheyenne Wells, where the tumbleweed midstream's up there. You get a little bit more pressure and nitrogen and stuff up there. I think they're pretty much related. I mean, I don't know. I think it's probably some long distance migration, also probably out of the Anadarko Basin, maybe. The problem is there's just not a whole lot of well control to really nail that down. And I'll show you too. I'll go to the map real quick. And appreciate everybody kind of sticking on. If y'all need to go to, you're not going to hurt my feelings. Right. So all of these, you can see this higher helium as you get up into Kansas. So here's the Oklahoma Panhandle right here. So this is all Cheyenne Wells. So this is pretty obviously, I would say, either long distance migration out of Kansas or maybe some migration out of the DJ too. All the Model Dome stuff is way out here. If I had more data, I'd love to find more data in here to see if that's actually, if we could actually connect up maybe the Keys field to it. But it's tough to say. I think it's probably coming out of Anadarko. So I don't know if that helps or not.
All right. And what looks like so far, the last question from Jim Tucker. Although out of the area you discussed here, is the helium occurrence in southeast Wyoming sourced from mineral decay, or is it juvenile via the kimberlites?
I would say it's probably from all of it is radiogenic, like very, very long, like deep time. So again, probably, I think the big thing that you see with all these is you're seeing high helium in very old reservoir rocks that have really good porosity and permeability and are typically water wet when they're not in a structural trap. So I think, again, just kind of reiterate is that you're probably degassing deep in the basement. It's moving up through these brine systems that are moving through these really high porosity permeability carrier beds. And then when it gets to shallow depths, then the helium will actually exsolve out of solution. And if you've got a trap there, you get a nice little helium trap. And if you don't, you don't. That would be my kind of go-to answer for that. As far as intrusions and kimberlites and stuff, you don't really see high helium with stuff like that. The exception being like a Shiprock field in New Mexico, which is a whole nother thing in itself. So that's a CO2 related field as well. So it's kind of a different beast, different animal.
Gotcha.
So,
well, I think that kind of wraps up the Q&A for now. And as you can see here on the screen, Bryan's contact information, please feel free to reach out to him. For those who want to rewatch this video, as we always do, Bryan has agreed to have this video published to the HGS YouTube page. So that usually takes about a month before we publish that video. But with that, I want to thank you, Bryan, for taking the time to and agreeing to present and share with the audience. I think had a good turnout, and I think we had a lot of fun learning about the things you did out there.
Yeah, appreciate it. And sorry, Mike. Yeah, appreciate it. And thanks everybody for joining. Like I said, if y'all got any questions, please feel free to reach out.
Yeah, thank you so much. And just once again, without our sponsors, events like this would not be possible. And I just want to bring up very briefly both Sizeware. Check them out if you haven't heard of them or used them. But they've been a good supporter of the HGS technical series, these luncheons and dinners. And Bryan here, Natural Gas Data Group, sponsored this talk. So please take a look at them and reach out to Bryan. With that, I want to go ahead and end the event, guys. And thank y'all so much for tuning in. Stay tuned and keep looking on the social media for HGS for the next events coming up. Thank y'all very much, and y'all have a good day.
Thank y'all.